Alright, so further proofs. Alright, so now in your question paper, this is the 1. You can change that to a 2. Otherwise, if it's a 1, it's going to be very straightforward. Okay, we don't really want that. We want something a bit more complex in there. Okay, so we need to find the coefficient of x to the power 3 in that expansion. Okay, so a couple of ways you can do this. One, you can obviously expand the whole thing out. Okay, and then group it all and factorize and all that sort of stuff again. Okay, or using your term, what you know about the term, we can reduce the amount of work. So any suggestions on what I can do here? Right, for the expression on the left hand side, what powers of x will I get if I were to expand that?
X squared.
Alright, so we've got x to the power 0, x to the power 1, and x to the power 2 for that left hand side. Okay, now if I want the to match it to get the coefficient of each of those sides of x to the power 3, if I've got x to the power 0 for the expression on this side, what's the power I need on the other side? X to the power 3. So if I've got x to the power 1 on the left hand expression, what's the one I need on the right hand side?
5, 4, 2.
Which one? 2? Because if I multiply those powers, I multiply with those terms for those powers, all I have to do is add the powers together. Okay? So if I got x to the power 2 on the left hand side, what do I need on the other expression? Okay? X to the power 1. So if I find the coefficient of those three groups there, I've just got to multiply and then add them all together at the end. Okay? So for x to the power 0 on the left hand side, I'll need the first term, so where k is 0. Alright, so I'll need, x to the power 0, I will need 2c0 of 2 to the power of 2 take away 0 times x to the power 0. Alright, for that left hand side. And then x to the power 3, I'll need that fourth term. In other words, k is 3. So we have 8c3, 1. Now I don't need to expand that because that's just going to be 1. And then x to the power of k, which is 3. So these two terms are going to be 2 to the power of 2, which is 4. And then we're going to multiply that by 8c3. Okay, x to the power of 1. So now I'm going to set k as 1 for that left expression. It will be 2c1 of 2 to the power of 2 take away 1 and x to the power of k. So I've got my x there, and the coefficient is going to be 2c1 times 2. And then x squared in the right hand side. Okay, so I now set k as 2. So 8c2 of 1 is still going to be 1, x to the power of 2. Right, so really we are expanding, but we're just focusing on the x to the power of 3 term, the coefficients of that. So instead of expanding the whole thing out, I can just use what I know about each of the terms, using an appropriate value for k. And then all I need to do now is add them together at the end. Power of 4 plus 2 lots of 2 C2 plus 1 C1, which is 8. Plus 4 plus 28 plus 8. 20, 48, 56. Should be the coefficient. I've done everything correctly then. Okay, so remember we can expand the whole thing out. Okay, so use your binomial theorem, but you're going to have 3 terms to deal with that and 9 terms to deal with that. Okay, so rather than trying to expand the whole thing out, or you can select cleverly what you need to expand. Okay, but if you look at it this approach, it should save you quite a bit of time. Okay, any questions on that? Right. Given that the binomial expansion is 1 plus x to the power of n, we just write that in sigma notation so we understand what the notation is there. Yep, okay, so we need to show this result here. So n, the sigma sum from k equals 0 to n of n c k of 2 to the power of k is equal to 3n. So remember, nk is another way to write your combination there. Alright. So, any ideas before I start it? Can you see anything? Great.
So easy.
Well, not 2. Ah, yes, 2, sorry, yep. Because everything here, this matches that, doesn't it? Yeah. Yeah? Okay, and then that means this must match this. Okay, so sometimes all you need to do is just make a suitable substitution. Alright, so let x is, what was it, 2? Yep. X equals 2. So 1 plus 2 to the power of n must equal sigma sum from k equals 0 to n of n k x to the power of k. Just to formally write that. Okay, that's all it is. We like it when things are nice and straightforward. Right, so this one. So we've got the same setup. So we've got 1 plus x to the power of n. We write it as sigma notation. We're going to show that the sigma sum from k equals 1 to n of k times nck is equal to n times 2 to the power of n take away 1. So, what can you see is what we need to do?
You need to get rid of the extra power on that side.
Get rid of it.
Do it on the left-hand side of the equation.
So how are we going to do it though?
Divide.
Hey?
Divide.
No. too, no? Where have you seen this happen before? What have you done in the past that's resulted in that? Starts with D. Yeah. Alright, so 1 plus x to the power of n is going to equal the sigma sum from k equals 0 to n of nk x to the power of k. So we've got n 0, x to the power of 0 which is 1, plus n 1, k is now 1, x to the power of 1, so it's just x, plus k is 2, x to the power of k, so it'll be x to the power of 2, plus dot dot dot, plus n, x to the power of n. You don't really need to write n because n is 1, however, just formally covering it. Okay, so differentiate both sides. The left-hand side, remember the product rule, function of a function in Intro to Calculus and Prelim. Okay, so bring down the power. Take 1 off the power and multiply it by the derivative inside the bracket. Okay, it was way back in your prelim course. It seems quite a while ago now. Okay, so the derivative inside the bracket's 1, so I don't need to modify that at all. When I differentiate NC0, what am I going to get? Differentiate. Well, what is N0? NC0 is going to provide a constant number. Yep, so when I differentiate a constant number, I get 0. Okay, because there are no x's here at all. So when I differentiate that, I'm going to get 0. When I differentiate NC1 times x, what's my derivative? Okay, so whatever that value is going to be in front of x. Okay, NC2 of x squared, when I differentiate that, I get. So I'm going to bring the 2 right at the very front. Right, I'm going to go an extra term. Alright, so the next one would be, up here will be NC3 of x cubed. Okay, so when I differentiate that, I'm going to get what? 3NC3 of x squared plus dot dot plus n outside of NCn x to the n take away 1. When I differentiate the last term, whatever the value for n is. Alright, so we've got this power now matching here, and we've got this side we need to write back as a sigma sum. Okay, so equal sigma sum well, can you say that if I have this, if I put it into this form and I expand it out, I'm going to get that. But I've got x's there as well. Alright, so if I go k equals 1 to n of my n k, I'm starting at 1 because I'm observing my first term here is 1. And then, really out the front, I've got the coefficients 1, 2, 3, 4, which will correlate to 1, 2, 3, 4. So k. And then I've drew up my x term to the power of k take away 1. Okay, because there's no x's here, so I need to do 1 take away 1 to get 0. And x of 1 for the second term, so k equals 2, so I need to take 1 off to just get k there. Alright, so almost finished. What do I need to do now? Alright, because I've got this part and that part in the right hand side, but I've got a 2 in between. Alright, so if I make x equals 1, I'll get that to 2. And then on this side, I've got all this, but I've still got the x to the power of k minus 1. So if I make that 1, 1 to the power of any number is still going to be 1 except for 0. Well, it's still going to be 1, technically, yes. Okay, so if I make x equals 1, okay, so imply the n 2 to the power of n take away 1, which is going to be the sigma sum of k equals 1 to n of k outside of n c k times 1 to the power of k minus 1. We can just leave this 1. Do you have any questions? Okay. Right, this one. A little bit more complicated. This doesn't really give you an obvious hint as to how to start. Right, so I've just expanded this part of it out. We need to show that now the hint here is going to come from that section there. Right, so where was saying before that on the denominator of a fraction I'm having n plus 1. In relation to x to the power of n. If we integrate x to the power of n, yeah? So what we're looking at is this bottom result here. I know if I integrate x to the power of n, I'm going to get the denominator of n plus 1. Alright, so that's going to be the hint in the question what you need to do. Alright, so let's integrate both sides. Now that we've covered integration, like I said, we can now do some of this question. Okay, so we haven't quite formally covered it in mathematics yet, but the integral of 1 plus x to the power of n, the 1 plus x to the power of n plus 1 over new power. Now there is actually an extra step when we're integrating. We need to also divide by the derivative inside the bracket. But we haven't covered it yet in mathematics. Alright? But because the derivative is 1, we can just leave that there for now, and we'll cover it formally this week in mathematics. Alright, what is the integral of NC0? So,
1.
well, NC0 is 1, yes? What is the integral of, let's say, 3? 3x. So what's the integral of NC0? Okay, and just to recognise the pattern, we're just going to write NC0 again. Alright, what's the integral of NC1 of x? Divide by new power, yep. Alright, what's the integral, the primitive function of NC2 of x squared? Over 3. Plus, dot, 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 plus n x to the k, there should be n here, n plus 1 all over n plus 1. And this is a indefinite integral, so what do I need to add at the end? Constant of integration, because we have no set condition to determine what the value is. Okay. However, with a smart substitution, I can make now for x, I can make the value for c very simple. Okay. Suggestions what that value for x is going to be. Zero. Okay, so if I make the substitute as 0, I'm going to eliminate all these terms here. I'm going to have the value for c as what's over here. Okay, so Alright, so this is just one arbitrary value we can have. We can substitute 1 if we wish. However, you can have lots of complicated, not complicated, but lots of terms involved with the constant. Because if we substitute 1, we're going to have an infinite sum because we don't know the value for n. Alright, so we make things really simple. We'll make it 0, eliminate everything else. So we got 1 to the power of n plus 1, which is just 1. 1 over n plus 1 must equal 0, because that's going to be the sum of all those n plus 1 terms plus the constant of integration. Okay, and that's going to be c. So, 1 plus x, n plus 1 over n plus 1, should we be writing that? Equals. So now I need to write this part here back into the sigma sum, because that's what the question is requiring me to do. Okay. So, you'll note in the question that we've changed from n's to r's. Okay, so because we've integrated, we're going to start at 0, go up to n again. Alright, so we look at this first term, so what r is 0, that's why I've started at 0 here. Okay, x to the power of 0, if I just left that as an r, but because we've got the x there, I need to add 1 to 0. Alright, so it'll be n r, x to the r plus 1, because I need to have x as to the power of 1 for the first term. all over what? Okay, so you're almost considering your last term here and replacing that with r's. Okay, so sigma sum of all your n plus 1 terms there, and then we need to substitute in for the value for c, 1 over n plus 1. Right, so we're not quite got what got up there, but we're on the right track. So what I'm going to do now is bring this over to that side to get this the subject of our equation. So sigma sum of r equals 0 to n of n r x to the r plus 1 over r plus 1 equals 1 plus x and then we bring this over to the other side, becomes a negative. I'm going to subtract it there. Now luckily we have the same denominator, so we can do the subtraction of the numerator. Right, so going back to the question, we notice here we don't have any x terms. Right, so again we need to make a clever substitution for x. What am I going to make for my substitution? Well, if I make it 0, I mean everything on this side will disappear. Hey? Good, why? Yeah, so if I substitute here negative 1, that's this part of it here will go to 0. So, make sure you let them know. So let x equals negative 1. And sigma sum of r equals 0 to n of nr minus 1 to the r plus 1 all over r plus 1. Okay, and then substituting for negative 1 here, so we've got 0 for all this. 0 to the power of n plus 1 is still going to be 0. So we're left with a minus 1 over n plus 1. Alright, we done? No. Hey? Yep. And what else is... So yes, if we remove the negative here, what else is different to what you've just got in your last line compared to what you need to show? Yep, we've already dealt with that though. There's no x's here. Yeah, alright, so this is r plus 1 here, and this is r, up there. Alright, this is a negative 1, and we want positive 1. Okay? So, thinking about this, every second term, or every second, not necessarily starting at 2, 4, 6, 8, it depends on the value for r, right? But what can you tell me about every second term in here? Negative. So you're going to have a pattern of positive, negative, positive, negative, or negative, positive, negative, positive, depending on the value for r, where you start. Okay? In other words, for the expansion. Alright, well, yeah, really r is 0. So the 0 plus 1, which is 1, means the first term is going to be negative. Okay? Now, I can alter that because that's where the negative comes here. If I alter this power to start at r instead of r plus 1, okay, that means the first term is going to be positive, isn't it? Alright, so therefore, r equals 0 to n of -1 to the power of r over r plus 1 must start with a positive because r is 0. Yep. Oh, I forgot the n, sorry. Times n cr, sorry, put that there, must equal 1 over n plus 1. So that means if you add from r equals 0 to whatever value for n is, and you add all these terms here, it's going to equal whatever the value for n is, 1 over n plus 1. Yeah, so if I make n is 10, and I add the first the 11 terms associated with that, it's going to equal 1 over 11. Okay, if I make that 100, if I have the first 100 terms, r equals 0 right up to 100, okay, and I add all them together, it's going to be 1 over 101. Okay, one of the topics you'll be doing is what's called mathematical induction, and proving that a series is consistent, or the sum of a series is consistent with this sort of thing. So how do you know what the sum of all this is going to be? That's the result, and we'll look at that in the topic of mathematical induction, which is a lot of fun.
Is that extension 1?
Hey?
Is that extension 1?
Yeah? Yep. Alright, any questions on that? Alright, find the values of constant k and n, so that the expansion of 1 plus 3x plus 3x squared all over 2, 3x squared over 2, all to the power of 4, and 1 plus kx all to the power of n, agree as far as the term as x squared, the term in x squared. Okay, so in other words, the terms for x 0, x1 and x2 are consistent if you were to expand both those sides. Alright, so let y equals 3x plus 3x squared over 2. Alright, just making things a bit easier for myself for the binomial expansion. So that means that 1 plus 3x plus 3x squared on 2 all to the power of 4 is 1 plus y to the power of 4. Okay, so I've just made these two y, so that I can make it easier for myself with expansion rather than trying to have 3 terms, because it's not a binomial expansion. It's trinomial expansion, I think it's called. Okay, so 1 plus y to the power of 4. So we can expand that much more straightforward than trying to expand all that. 1 plus, what's the next coefficient? Do you remember? 4. 4y plus 6y squared. And we've got symmetry. 1y to the power of 4. Okay, now we only really need to consider a certain amount of terms. We won't need to consider the whole thing because we just need to look at up to the powers of x squared. Alright, so we just need to be careful what we do. Alright, 1 plus kx all to the power of n. Okay, so we need to determine the value of k and n so that the coefficient, the terms, the expansion are going to be consistent with what we got up to x squared, depending on our substitution. Alright, so n c0 so we don't know what the value for n or k is at the moment. 1 to the power of n take away 0, which is still 1, and then k x to the power of 0. Right, so we can't do any more of that. Plus nc1, 1 to the power of n take away 1, so it's still 1, and then you've got kx to the power of 1. nc2, again 1 to the power of any number is still 1, and then kx to the power of 2. Alright, I can stop there because I just need to go up to as far as the term x squared. Okay, so I've expanded this up to the term of x squared, so now I can start matching some coefficient. Alright. Works in my mind, just trying to work out a way to explain it to you guys. Alright, so we need to consider, let's consider this, power of x to the 1. Alright, so we need to consider this with what's up here. So maybe we should make a substitution, make it clear for you guys. So let's call this number 1 and number 2. So put number 1 into number 2. Alright, I'm not concerned about the left hand side now, just concerned about the right hand side. So 1 plus 4 lots of all that. Right, so I only need to go up to that term there. Because if I do the expansion of this squared, the lowest power I'm going to get is 2. If I do the expanding the perfect square, the highest power I'm going to get is 2. Alright, so because of that I don't need to go any further. Alright, because if I do this to the power of 3, it means the highest power, the lowest power, sorry, is going to be 3, and it's just not going to become any useful information for me. Okay, so we need to consider the coefficient of x and match it with the correct coefficient of the x term in that expression there. Okay, so this is the only term here, when I expand the whole series out, that's going to be the only term involving just x. Did you follow that? Did you? Right, now because of that, the coefficient of this would match the coefficient of this, wouldn't it? So, nc1 of k must equal 4 times 3. And what's nc1? Yeah. nk is 12. Okay, Okay, so I have one equation, two unknown. Okay, so I can't just state a value because they can have an infinite number combination to make that work. So what I need to do is also do a similar thing for the x squared term because they agree, it means they are the same. Right, so NC2 k squared, so we just need to compare the coefficient because we know the variable x is still the same. And in how many places have I got x squared in this expression here when I consider expansion? Two. Okay, because if I expand this part here, that's going to give me an x squared term. And just first part here, when I expand my square here, my perfect square. Okay, they were the only two places that that will work. So, if I were to treat the expansion, it would be 4 times 3 over 2. Right, so 4 over 2 is 2. 2 times 3, just the coefficient, it's 6 if I were to expand that. Plus 6 times 3x squared becomes a 9x squared. So it'll be 6 times 9. So NC2, n factorial over n take away 2 factorial, 2 factorial, that's the definition of your combination. And 6 plus 6 times 9 is 60. Pardon? Yep, so k squared is that. Right, so number, not number 3 yet. So if we set k as 12 over n, so now we're solving simultaneously. So that's now 3, and this one is 4. So 3 into 4. So n factorial over n take away 2 factorial 2 factorial times 12 over n or squared must equal 60. Now we need to solve for n and then we'll get k. Right, so I've got n factorial over n take away 2 factorial. Now 12 squared is 144, and then we've got divided by 2 times 1, so 144 divided by 2, which is 72, over n squared is equal to 60. Right, so I've got factorials and I've got squares. Alright, any suggestions on what I can do to tidy that up a bit?
Get rid of the minus 2 factorial.
How?
All you have is n minus n minus 1.
Good. Alright, so n outside of n take away 1. So it will allow this to cancel. Because this is n times n take away 1 times n take away 2. Alright, and that's the starting point there. So we need those two left over on the numerator. All over, so 72, all over n squared must equal 60. Look at that, we've just got rid of all the factorial notation, and we can now cancel the n squared with the n on top. So 72n take away 72 must equal 60. Nice simple two-step equation there.
60n.
So,
What was 60n?
Oh, sorry, yep. Apologies, thank you. 60n. Okay, so bring the 60n on the other side. So it becomes a 72 take away 60, so 12n is 72. N equals 6. Put that into fully valued k. So number 3 means that k is going to be 12 divided by 6, which is 2. Right, question. So there's one more example. We'll do that on next Extension 1 lesson. I think that's the working lesson, is it?